Okay, problem 550. A nozzle is attached to a vertical pipe and discharges water into the atmosphere as shown in the figure. When the discharge is 0.1 meters cubed per second, the gauge pressure at the flange is 40 kilopascals. Determine the vertical component of the anchoring force required to hold the nozzle in place. The nozzle has a weight of 200 newtons, and the volume of water in the nozzle is 0.012 meters cubed. Is the anchoring force directed upward or downward? Okay. So let's jot down the givens that we have. Okay, we are told the weight of the nozzle. We're told that's 200 newtons. We're also told we have the volume of the water is 0.012 meters cubed. The discharge, or the flow rate, is 0.1 meters cubed per second. And we have the pressure at the flange, so I'm going to call that location 1. Okay, so that means P1 is going to equal 40 kilopascals, okay, which again is 40 times 10 to the third pascals. Okay. All right, so we have that. Now we're going to be doing a conservation of momentum analysis on our control volume. So let's first try and draw out what our control volume would be. So I have information at that flange. So that'll be one of my surfaces. I'm trying to find the anchoring force, so I include all of the nozzle itself. Okay. Then at the exit, I have some more information. So I put the end of my control volume in that location, and I always have my surface, my control surface, perpendicular to my velocity vector. Okay, so I'm going to have some velocity leaving. Right, I'm given the angle at which this is at. I'll call that v2. We have some velocity coming in. This I'll call velocity v1. Okay. So velocity coming in means it's going to be bringing in its own momentum. So we're going to have momentum coming in and momentum coming out. Aside from that, we have some weights. We have the weight of the nozzle, and we also have the weight of the water. Okay, so those are the body forces on this problem. Other forces that we have, well, we're told that there's a pressure at that nozzle at the flange where the nozzle meets the pipe. So there's going to be some pressure, right? So that pressure is going to be equivalent to some force P1 times A1. Okay, so we have the pressures, the weights, those are our surface forces and our body forces, and then we have the momentum flux terms. So we should be all set to go ahead and try and start our analysis. All right. So let's look at conservation of momentum. Let's do the momentum in the z direction, because that's, oh, I forgot one force. Let's go back, and let's also recall we're trying to find the anchoring force, right? This is going to want, the flow is going to want to push away that nozzle from the flange. So the flange has to hold that nozzle in. So let's draw some force. I'm going to call that the anchoring force in the z direction. Okay, and I'm just putting it in the positive or in the positive direction right now because I don't know what the value is. But when we do our analysis, we'll solve for that. Okay, so those are all of our forces. We'll go back to our z momentum equation. Okay, time rate of change of the momentum in our control volume. And that's going to be, for the z direction, W times rho dV plus the flux terms, W rho V dotted with N dA. And that has to equal the sum of the forces in the z direction. Okay? Steady state analysis, that derivative goes to 0. So that whole term drops away. And we're just left with the flux terms, the or the momentum that crosses my boundaries has to equal the sum of the forces. Okay? So let's work on that flux term. Okay, we said momentum coming in to our control volume is always given the minus sign. Okay, so we have minus, and we have W at 1 times the m dot at 1. That's the momentum coming in. And then momentum leaving, we have flow leaving at position 2. So leaving is a plus. We have W at 2 times the m dot at 2. And that has to equal the sum of my forces in the z direction. I have in the positive direction that anchoring force in the z direction. Then in the negative direction I have the weight of the nozzle. I also have the weight of the water. And lastly I have that pressure force that's in the positive direction. It's pointed upward. So that is P1 times A1. Alright? Okay. Continuing on. We have from continuity, okay, we know that m dot 1 has to equal m dot 2. Okay? And our incompressible version says that Q1 has to equal Q2. Okay? And that is A1 V1 equals A2 V2. Okay. All right, let's jot down a couple of notes. Let's note that my velocity V1 is purely in the vertical direction, right? We have purely in this vertical direction here, and that's in the W direction. Okay, so my velocity at 1 is just equal to W at 1. Okay. Now W at 2 is a different story because my velocity at 2 has some angle. Okay, and we're given that angle of 30 degrees. So we do a little trig and we find out that W2 is really just V2 times the the sine times the sine 30 degrees. Okay? Continuity tells me that V1 is going to have to equal Q divided by A1. Okay, we're given Q, that's 0.1. A1, we are also given, okay, we're given the areas A1 and A2. So A1 is 0.02. So you'll get 5 meters per second. And V2 has to equal Q times A2, which is 0.1 divided by 0.01, which is 10 meters per second. All right? Okay. All right, so that means W2 is just going to equal 10 times the sine of 30 degrees, right? So we can go back to our conservation of momentum. That said minus W1 times m dot 1 plus W2 m dot 2 has to equal F AZ minus Wn minus W of the water, the weight of the water, plus the pressure force P1 times A1. Okay. So we still need to determine what the weight of the water is. So let's do that now. We have the weight of the water. That's going to equal the density times the volume times the acceleration due to gravity. The density of water, 999. The volume of the water we were given, that was 0.012, and G, 9.81. So we can find that the weight of the water is 117.6 newtons. Okay. I'll find the pressure force, P1 times A1. That's equal to 40 kPa, 40 times 10 to the third, times the area at A1, which was 0.02. So that's equal to 800 newtons. And m dot, solve for that. M dot is rho times Q. So that's just 999 times the 0.10. So that's 99.9 kilograms per second. Okay? All right. So that seems to be everything. Now we can go and plug all these values into our momentum equation. Okay? So again, I'll write it since we just got rid of it. Minus W1 m dot 1 plus W2 m dot 2 equals FAZ minus the weight of the nozzle minus the weight of the water plus P1 A1. Okay? So the velocity coming in, W1, we said was all of V1, and that was 5 meters per second. The m dot, we said, was 99.9 plus W2, which happened to be 10 times the sine of 30 degrees, times m dot 99.9 had to equal F sub AZ minus the weight of the nozzle was 200 newtons minus the weight of the water, 117.6 newtons, plus the pressure force, which was 800 newtons. Okay. All right, one equation, one unknown. I can solve for FAZ, and I find that that is equal to a negative 482.4 newtons. Okay. So what does that negative sign mean? Initially, I had said that my force FAZ was in the vertical direction, so because I got a minus sign, it actually tells me that FAZ is actually down. So it tells me that that anchoring force is 482.4 newtons down.